Good morning to all of you, MSc Physics second year student. And today again welcome to lecture series on the subject Energy Studies second. And we want to continue our chapter which is the solar photovoltaics. In the last lecture already we have to see what is the introduction part and the part which is consist about what is the solar photovoltaics and what is the main types of the semiconductor. So, this type or this concept already see in the last lecture. So, in this lecture we want to see what is the idea of the p-n junction, or we have to note that so that the types of the semiconductor, and in those types of the semiconductor, so two types is there, n type semiconductor and p type semiconductor. What is mean by n type semiconductor? So that n type semiconductor which is considered as the majority charge carrier which is the electrons, and p type semiconductor which is the majority charge carrier which is considered as a hole. And these two type of semiconductor which is joined together, there a joining part or the boundary types or boundary level, there is a one of the junction made. So that is junction is made at the boundary, and the electrons from n type region will diffuse across the joining boundary in p type region, and similarly holes from p region will diffuse across the joining boundary in n type region. So that holes from p type region will diffuse across the joining of n type region. So that means that if you see in the schematic of the p-n junction, so that n type and p type semiconductor, so that n type semiconductor majority charge of these electrons which is diffused across the junction in the p type region, and the p type semiconductor the majority charge carrier, so that is diffused across the n type region. And this process of the diffusion which is will continue until the potential which is equal to sum of the diffusion potential of electrons and holes established across the p-n junction. And if you know that, so that as a result the permanent electric potential is established at the junction and known as the potential barrier. So this is the concept of the p-n junction. So that is considered that the formation of this diffusion depletion layer and that diffusion potential of electrons and holes is established across this p-n junction. So that is the result of this depletion region or diffusion potential, that is having a permanent electric potential is established is at the junction, and this junction, this electric potential which is established at the junction, so this area which is considered as the potential barrier. Okay. So and this p-n junction which is can be made by the various method, and this method such as implanting method, diffusing or growing n type impurity on p type crystal, or growing p type impurity on the n type crystal. So this is the idea about the formation of the p-n junction. Now we want to see the next concept of which is the absorption of light, and we have to know that what is the phenomena of the absorption of light or when it occur. The first condition which is considered when the light which is incident on a semiconductor having energy greater than the band gap, and it gets completely absorbed and utilized to electron hole pair formation or converted into heat. That means that simple. So that the whatever light which is incident on the semiconductor material, and that light energy which is greater than the band gap energy, so that type or this light energy which is greater than band gap, it gets completely absorbed. So that condition, this if we consider the incident light that energy or intensity of light which is considered this I naught, and after the absorption of light that have intensity which is considered that I, and this light which is completely absorbed. So that's why this light is absorbed, that in your semiconductor material there is the electron and hole there is a present, and this due to absorption of this light, this electron and hole which is get pair formation, or this is say that converted into heat. And the absorption of light in a semiconductor is of the two types of the absorption phenomena. First one which is considered as the direct absorption, and second which is considered as the indirect absorption. Or what is the basic idea, or what is the basic difference between the direct absorption or indirect absorption? Or if we see that the figure of this that is the optical absorption in the direct band gap semiconductor from the valence band to conduction band. So that is the direct light absorption process in the semiconductor. In this case, the photon momentum k is equal to h by lambda is conserved. The photon momentum k is equal to h by lambda is conserved. The absorption start at a photon energy that E is equal to h nu is equal to band gap Eg of the semiconductor. So that means that the photon energy is equal to the band gap energy of the semiconductor, and the electron which is transfer vertically from the valence band to the conduction band without change in momentum. So that's why we have to see that in the figure that the in the low side or that valence band and conduction band is there. So that is the transfer of electron from valence band to the conduction band is straight line, that is the vertically transfer of electron, that is does not change in the momentum of the electron. So if we see in the figure, so that the bottom level of the conduction band and top level of the valence band, so that is the gap between these which is known as the band gap energy, that is the Eg. And momentum k is equal to h by lambda, that also you know that, and Ef and Eb, so that is the energy level of particular conduction band and the valence band. And if we calculate this absorption coefficient, so that is alpha for this transition of electron from valence band to the conduction band, and that relation will get here. So that is alpha, that is the absorption coefficient, is equal to A star h nu minus Eg whole power 1 by 2, and here A star which is the constant, and that constant value which is 2 into 10 to the power 4, and this alpha which is expressed in the unit which is centimeter inverse, and h nu and Eg are in the electron volt. And the above equation we can be write or written as alpha square is equal to A star square h nu minus Eg, and this h nu that is considered as the photon energy is equal to h nu, that is the original energy for that considered as the light incident on the material, and Eg is the band gap energy. And this relation show this alpha square is equal to A star whole square h nu minus Eg. So when a graph between the photon energy h nu and alpha square is plotted, its nature is a straight line for the direct absorption, and this nature is shown in the figure, and the intercept on the Absorption photon energy axis. It gives the band gap of semiconductor material, and the semiconductor material shows the direct absorption of the light are called the direct band gap semiconductor. So that graph shows that photon energy h mu which is versus the alpha square, that is the absorption coefficient, and the nature of this graph which is the straight line, and this nature which is shown the band gap of semiconductor material, and this material shows the direct absorption of light which is called as the direct band gap of the semiconductor. And this example of the direct band gap semiconductor, which is considered as the gallium arsenic, CDS, that is cadmium sulfur, cadmium tellurium, or which is indium phosphorus, INP. So these are the example of the band gap semiconductor material. So that is the direct band gap semiconductor material. And next type we want to see here, that is the indirect band gap, or we have to know that idea. So in direct band gap of the semiconductor material, so that is the absorption of the process in the semiconductor, that in case that transfer of electron from valence band to conduction band, so that the photon momentum k is conserved. So that is the original energy E and band gap energy E is equal, and that is does not variation in the momentum k. Or if we see in the idea indirect band gap or indirect absorption of light, the process the semiconductor in case the transition of electron from valence band to the conduction band occurs at the different value of the momentum k. See the main difference in the direct band gap, this k momentum is conserved or same or equal value of the momentum does not change in momentum, and in indirect band gap it occurs that different values of the momentum k, and that k is equal to h by lambda. And if we see in the figure that the optical absorption in the indirect band gap semiconductor from valence band to the conduction band, and if we see that energy E conduction band, so that conduction band you have to know that idea. So that is the lower portion, or that is the lowest bottom of the conduction band and top bottom of the valence band. So that two types of the here momentum is there. So that is the many of the point of the lower bottom of the conduction band, that energy is absorbed, or that electron which is transferred from many other different direction. So that's why the your momentum also change, and this we have to know that the electron transition from valence band to the conduction band, which is shown in figure, and what type of photon absorption is there, and that change in momentum which is denoted by k. And EC and EV, that is the energy which is considered as the conduction band and valence band, and that gap between these two band which is considered as the band gap energy. And if we see that the transition of electron from maximum energy of valence band to minimum energy of conduction band, and this take place by the emission and absorption of photon of required momentum, and this photon has high momentum but low energy. This phonon has. So one of the concept is here, what is the main difference in photon and phonon. So first of all, that in terms of the phonon, so that has the high momentum and low energy, and hence minimum photon energy which is required to excite the electron from valence band to the conduction band. Okay, so what is main idea, that minimum photon energy which is required, the minimum photon energy is required to excite this electron from valence band to the conduction band, and this energy EP is the energy of phonon with the required momentum. Since the absorption process which is requires an extra particle, that phonon, the probability that the light being absorbed, the probability of the absorption this process extra particle, the phonon probability that the light being the absorbed, and in this process the much less than in the direct absorption process. And if we see the absorption coefficient which is less, and light can pass in the reasonable distance with the semiconductor which is prior to the absorption, and the total absorption coefficient which is given by alpha is equal to alpha A plus alpha E, and this alpha A and alpha E which is considered as the absorption coefficient due to phonon absorption and phonon emission. So that alpha A, which is considered as the phonon absorption, and alpha E, which is considered as the phonon emission. And in case the direct transition, it is given by alpha is equal to A star H nu plus EP minus Eg whole power 1 by 2. And if we squaring of this equation, that alpha square is equal to A star square H nu plus EP minus Eg. So main difference or that probability of question will be arise here, that MCQ type. So for the absorption of light in direct absorption or indirect absorption, what is the main difference? So that main difference in the direct absorption, that the momentum value which does not change, and in direct absorption, that this absorption of light which is occurs at the different value of k. These are the main difference in those direct and indirect absorption of light. And if we see indirect band gap, so that see the graphical nature, so that graph between the photon energy h nu and alpha square is plotted. We get two line segment, this nature which is considered as alpha E whole power 1 by 2, and due to the phonon emission, due to the phonon absorption h nu 1 and h nu 2, band gap phonon energy, the graph of absorption of coefficient as a function of the photon energy. And if we see that h nu 1, that is energy E1, h nu 2, that energy E2, and due to absorption and emission or phonon absorption, so that have give the idea that if we see in the figure, the upper line segment, so that is the intercept of the h nu 2 on the photon energy. So in this, due to that h nu 2, that is the segment intercept on the photon energy axis, which is corresponding to the emission of a phonon, while the lower segment intercept corresponding to the absorption of the phonon. So the midpoint of the intercept h nu 1 and h nu 2, this gives the, this is the midpoint is there, so that is the band gap, and that midpoint which is intercept of h nu 1 h nu 2 gives the indirect band gap of the semiconductor. And this semiconductor shows the indirect absorption of light is called the indirect band gap of semiconductor. The example of indirect band gap of semiconductor, which is the silicon, aluminum, arsenic, etc. This type of, that is the examples of the indirect. Now next lecture we want to see the idea of the what is the formation of the p-n junction by the diffusion process, and which type of the diffusion process is there, and solar cell metal contact formation, and how to develop the solar cell or solar plate, how to develop the solar cell to the solar cell module panel array. So this type of concept will be seen in the next lecture. So thanking of you.